So in this video, I want to think about how we go about finding the margin of error. How do we find our margin of error? How do we calculate it? So the margin of error, E, should be defined as the difference between the predicted proportion and the actual proportion. So in other words, I'm saying really what the error is the difference between our point estimate and the actual value of a proportion. Now this is if we're talking about estimating the population proportion as opposed to the population mean, then again, our error should be the difference between our predicted value for the proportion and the actual value of the proportion, the difference between the statistic and the parameter, in other words. The only trouble is we're not going to know what the true parameter is. If we knew the true parameter, then we wouldn't need to be estimating it with a point estimate. So we're not going to know this value, so we can't calculate the margin of error this way. We need to come up with some other way of doing that. So the way we're going to do that is by thinking about a normal distribution. Now, we know that we can find a z-score by taking a data value minus the mean and dividing by the standard deviation. We also know that if n times p times 1 minus p is 10 or bigger, if we know that that's true, then the distribution of p hat will be normal. So the p hat distribution will be normal. So I want to think about that using this idea. So if I'm dealing with a p hat distribution, then the z-score for a p hat distribution would equal p hat minus the mean of the p hat distribution divided by the standard deviation of the p hat distribution. So this is the z-score for a p hat distribution. So if that's the case, if z equals p hat minus the mean of the p hat distribution divided by the standard deviation of the p hat distribution, which again is really just the formula for finding a z-score, well, remember that the mean of a p hat distribution equals p, and the standard deviation of the p hat distribution equals the square root of p times 1 minus p over n. We studied that when we were discussing the sampling distribution of p hat in the previous chapter. So this is true. So if z equals p hat minus the mean of the p hat distribution divided by the standard deviation of the p hat distribution, and if this is equal to p, and if this is the square root of p times 1 minus p over n, then what I have here is p hat minus p over the square root of p times 1 minus p over n. So this becomes this when I recognize that the mean of the p hat distribution is p and that the standard deviation of the p hat distribution is the square root of p times 1 minus p over n. So that means then that if I take p hat minus p, that should equal z times the square root of p times 1 minus p over n. So p hat minus p equals this z-score times the square root of p times 1 minus p over n. And again, that's what we said the error should be. So this would be a good formula for error. The error is going to equal some z-score times the square root of p times 1 minus p over n. Well, what z-score? Well, that z-score is going to depend on the level of confidence that we're using. So, for example, if here is a normal distribution, so here is a z-score, so that this total area in the two tails is alpha. So if the total area in the two tails is alpha, then that means this area in between the two tails is 1 minus alpha, and that's what the notation is that we've been using for our level of confidence. So this z-score right here and right here, this would be negative z sub alpha over 2, and this would be positive z sub alpha over 2. So alpha over 2 would be the area in this tail, and alpha over 2 would be the area in this tail. Again, if the total area in the two tails is alpha, we're defining that, then that means half of alpha is in this tail, half of alpha is in this tail, and so that's going to give us z-scores that's connected to this level of confidence. So our real formula is going to be that the margin of error is going to equal z sub alpha over 2 depending on the level of confidence that we're using. So if we're using 95% level of confidence, then we're going to get one set of z-scores. If we're using 90% levels of confidence, then we'll have different z-scores for that. And same for any level of confidence that we use. And there's one other issue, and that is we're not going to really know what p is here. So what we're going to use instead, which is going to cause a little bit more error potentially, but we're going to use p hat in the place of p because we don't know what p actually is. But it turns out that that doesn't cause a significant amount of error because regardless of what p hat is or what p is, this calculation can't vary too much. So this is the idea of where our margin of error formula is going to come from. And so we're going to formalize that on the next sheet. So definition, the margin of error E in a 1 minus alpha times 100% confidence interval for a population proportion is given by E equals z sub alpha over 2 times the square root of p hat times 1 minus p hat over n. So this is the exact formula that we just developed on the previous sheet. And so again, the specific z-score here is going to depend on what alpha is, and alpha depends on our level of confidence. So we'll see an example of that in just a moment. So if we're going to construct a 1 minus alpha times 100% confidence interval for a population proportion, then here's how we're going to do that. Suppose that a simple random sample of size n is taken from a population, or the data are the result of a randomized experiment. So we have randomization. Either we're selecting a sample randomly or we're doing a randomized experiment. A 1 minus alpha times 100% confidence interval for p is given by the following quantities. The lower bound of our confidence interval is going to equal p hat, our point estimate, minus z sub alpha over 2 times the square root of p hat times 1 minus p hat all over n. Now again, that right there is the error. So what we're really doing is taking p hat minus the error, and then the upper bound is p hat plus z sub alpha over 2 times the square root of p hat times 1 minus p over n. Again, that's really the error, so we're doing p hat plus the error. So in other words, what we're really going to be doing is we're going to be taking p hat minus our error, we're going to be taking p hat plus the error, and that's going to give us our confidence interval. And we will be 1 minus alpha times 100% confident that the true parameter p will be inside that interval. Now, one last point that I need to make. All of this is based on the normal distribution. So in order for these formulas to be true, any of these, we have to have a normal distribution. And what we're really talking about here is a distribution of p hat. So as we learned in the previous chapter, the p hat distribution will be normal if n times p times 1 minus p is 10 or bigger. So we have to check conditions. So note, it must be the case that n times p hat times 1 minus p hat is 10 or bigger in order to be able to say that the p hat distribution's normal. Now again, technically it should really be p here, so it should be n times p times 1 minus p, but we're not going to know what p is, so we have to use p hat instead. Now, This means, again, that our sample size has to be big enough in order for this condition to be true. But we also have to have independence. So the individuals in our samples have to be independent from one another. And so in order to verify that independence, our sample sizes can't be too big. So as a general rule, we say that the sample size has to be less than or equal to 5% of the population. So the sample size has to be less than or equal to 0.05 times the population size. Both of these conditions have to be met. N times p hat times 1 minus p hat has to be 10 or bigger, and the sample size has to be less than 5% of the population in order to construct this interval. And then one more time, just for emphasis, what we're looking for here is independence. The sample size has to be less than 5% of the population in order to ensure independence. And so that's why we have to check that condition. So I think this will all come together and make sense with an example. So we're going to look at our first example in a new video.